And we do some highlighting and formalize what we saw. Here we go, highlighter. First thing we're going to look at is adding fractions. And a couple of things, like we already talked about, all we do is add the y values. So if we look at this point, 2, 2, and the blue point, 2, -1, if you added those together, you would get the green point, because you add the y values, and you get 2, 1. So when we're adding functions together, we just add the y values. However, I find that there is some new notation here.
Bonjour tout le monde. Hello everybody. Today it's
I'll pause it and we'll start it again after. So the big thing here is notation. The idea of adding two graphs is you just add the y values. Notation wise, you could have something like this. So I could say, what is f of 2 plus, and I'll color code it here. No, that's g. I'm trying to color code it. G of 2 plus f of 2. And g was the blue graph, and f was the red graph. So g of 2, well, that's its y value, it's -1. Plus f of 2, its y value was 2. This would equal -1 plus 2, 1. And that's why we have the point 2, 1 on the green graph. Now, often what happens is you have these two different notations, and this second notation is harder to work with. So you could get the following question. What is f plus g of 2? And if it was written this way, what I would suggest is this means f of 2 plus g of 2. I like this second notation. I think it's much more intuitive, but they use the first notation sometimes as well. So if you see f plus g of 2, this means f of 2 plus g of 2. Okay, and we're going to see it in multiplication, we're going to see it in subtraction. Some other things that we've noticed already. The green graph, the domain of the green graph is the overlap of the domain of the red and the blue graph. If one of the graphs doesn't exist, you can't add the other one at that point. So for example, at -3, there's no red graph. So there's no green graph at -3 either. You can only add them up. And that's why they have this domain here. They say the domain of f of x was x is bigger than 2. The domain of g of x was everything, but then adding them up, it's just where the domains overlap, and it's only where x is bigger than or equal to -2. That's adding. Next, subtracting. Take out our highlighter again. Okay. And highlight the not nice notation. So if you were ever asked to do f minus g of some number, change it to nice notation. This means f of x minus g of x. So just to be aware of that notation, because sometimes on an exam, you get a notation you haven't seen before, all of a sudden you feel like you can't do that question. So this f of 2 minus g of 2, this could have been written as f minus g of 2. Putting them together, you are going to get 2, 3. Again, the domain is where both of them exist. So since the red graph only exists when x is greater than or equal to -2, the same thing happens with the green graph. Multiplying functions. We got our highlighter. The not nice notation can come in a bunch. I've seen, wow, that's yellow. I have seen this, I have seen This is my absolute not favorite. They have like one font for this X, and I tried to make different looking fonts. I think my second X just died. It's really bad. Oh, it shows on my hand. Okay. Can't even cover it up. Like, they use that kind of X. Sometimes I've seen it just with them beside each other. Like, all of those are the not nice notation. If you see the not nice notation, all of these mean f of x times g of x. That's much nicer to work with. So if I did f of 2 times g of 2 and multiplied that out, I would get -2. And we talked already about some of the strategies for multiplying. One strategy is look, wherever the red graph or the blue graph is 0. Those are easy things to multiply. Do you see that at that red point and that blue point, the green graph is also going to be 0. That's a good strategy, to use points where it's 0. It's also a good strategy to use points where one of the graphs is 1. Do you see that the red graph is 1 here? And the blue graph is 1 right there. And sure enough, the green graph at that point is exactly the same as the other one, because 1 times anything would be whatever it is. And here, it's right on the red graph. So you can use that as a strategy to find 2 more points. So 0s and 1s, that got me 4 points already. And those 4 points, if I had those 4 points, does it make sense that I probably could draw this section? Not too bad. And then any other nice points, like here, 2 times -1, that point wasn't hard to figure out. You can also use some of your skills. A positive times a negative is going to be negative. Does it make sense that where the red graph is positive and the blue graph is negative, when you multiply them together, the green graph should be negative? Negative times a negative would be positive. So if both graphs are below, when you multiply them, your green graph would be above. Same idea with domain. It's going to be the overlap. Now we're going to do the dividing one before we do example 1, just so we've done all of them together. And this one, let's add a title. This is on the top of page 275. All the other ones had titles, and I highlighted them. This one didn't have a title, so I'm going to write it, and I'm going to highlight it. This is our dividing functions. Dividing functions is the most complicated. It also has not nice notation. Here are examples of not nice notation. This, I've seen this, I've seen this, I've seen this. All of these, I would rewrite them. They all mean f of x divided by g of x. So you might get the following. What is f divided by g of 2? And the first thing I would do is I would rewrite it as f of 2 divided by g of 2. Figure that out. 2 divided by -1 will be -2, and that finds our other point. But with dividing functions, we have some weird things happen. First of all, I'm going to color code here a little bit. The function we're doing is we're doing f of x, which was my red one, divided by g of x, which was my blue graph. So some important things that happen. Look, where your blue graph is equal to 0, that would be a non-permissible value. Non-permissible values either end up with holes or vertical asymptotes. Almost always in this unit, they end up as vertical asymptotes. The only way they end up as holes is if your red graph and blue graph crossed each other right on the x-intercept, then it'll probably be a hole in your graph. But if just the blue graph is equal to 0 and not the red graph at the same time, then it will be an asymptote. So that's going to be important. Now, where your red graph is 0, right? If the top of your function is 0, that's an x-intercept, right? 0 divided by anything is 0. So notice that our green graph shares that point. If you have nice points, like here we could do 2 divided by -1 and get -2, no problem. Okay? With dividing, you will also cheat as much as you can and use your chapter 2 knowledge. The red graph is a square root graph. A square root graph has an x to the half, right? The blue graph is a line. In fact, this looks like it's minus x plus 1, y equals mx plus b. This is group 3. What's the degree on the bottom? The degree on the bottom is a 1. The degree on the top is a half. When the degree is bigger in your denominator, what did you know about your graph? It had, oh, it should be red. It will have an asymptote at y equals 0. So we have to use some of our skills in the dividing one for sure from previous units to help us graph. Okay? Next, wherever a graph is 1, it could be easy to figure out. So I'm going to start with the red graph. The red graph is 1 there. The blue graph is 2. 1 over 2. The green graph is a half. Here the blue graph is 1. If you divide by 1, you see that your green graph will be exactly the same as your red graph. So where the graphs are 1 are also points that you can think about. Okay? Domain and range. The domain of f of x is bigger than or equal to 2. The domain of qx was, and g of x is everything, but q of x is also going to be the overlap, plus we have to add the non-permissible value and take that out. And then once you've got a couple of points, you draw it towards your asymptotes, and you'll have your graph. So the dividing one, probably the most complicated. Okay, let's go to example 1. Ooh, it's got a nice tough one to start with. F of x is x plus 2. G of x is the absolute value of x. So in your head, you're going to use this last chapter really uses all of our skills from previous chapters to really do things. So I see x plus 2, and I think to myself, okay, that's a straight line, slope of 1, y-intercept of 2. I draw a quick little picture of it. I also think g of x absolute value graph. My absolute value graph looks like this. So I have an idea of both of my graphs already. State the domain and range of both f of x and g of x. Okay, so f of x, that's my green one, I'll do that in green. Domain is everything, range is everything, and my blue graph, the domain was everything. and my range was bigger than or equal to 0. Now h of x in part B is f of x plus g of x.
What's wrong?
I don't know why it's having. Yeah, it's struggling. It's struggling today. H of x is of x g of x. So now you'll think the audio is going to just try and act it out. Write an explicit equation. This is going to be something. Okay. Explicit equation is really easy. It just means in terms of x. So what we do for the explicit equation here is we say h of x, instead of writing the function notation, f of x, we write x plus 2 for f of x, and we write the absolute value of x for g of x. This would be an explicit equation. Now the domain we can figure out from this one easily because the domain of the first two was everything. So the domain of h of x, when you add them together, will be everything. But the range is a little tricky. You almost have to do the graph to figure out the range. So in this graph, if I start adding these graphs together, I'm going to have the following results. I'll do this one in purple. So I look at my original graphs. Do you see that you would have at 0, you have 0 plus 2, so I'll have 2 there. At 1, I would have 1 plus 3, I would have 4. At 2, I would have 2 plus 4, that would be 6. I could go to my equation, just do the mental math. At negative 1, I would have 1 plus 1, I would have 2. At negative 2, I would have 2 plus 0 would be 2. At negative 3, I would have negative 1 plus 3, because the absolute value would make it positive, would give me 2 again. Well, this is kind of interesting. Those are all flat. Are they always going to be 2? Go back, minus 4. Does minus 4 give me 2 again? Yes. So it seems like, I've added some, it seems like it's flat here and like this, so my range is bigger than or equal to 2. Now I'm going to introduce something to you that you'll see in AP Calculus. Something called piecewise functions. This purple graph is a piecewise function. It has 2 pieces. Do you see that 2 straight lines have been connected together? One of them is flat at 2, and one of them has a different slope. And so it's the flat part at 2 when x is less than 0, and it's the slopier part when x is bigger than 0. And when you can only define a function as 2 different pieces, it's called a piecewise function. The most common piecewise function that we actually write is, and it's written here, is g of x. I'll do this for you. G of x was the absolute value of x. And you know the absolute value of x is really 2 straight lines grouped together. And so when we write a piecewise function, we can write g of x like this. Big fancy squiggle bracket. And we write both parts separately. Do you see that this part is y equals negative x? It has a negative slope and goes through 0. And this part is y equals positive x because it has a positive slope, but also still has a y-intercept of 0. Those would be the two lines. I mean, y equals negative x would keep on going, right? Like this. And y equals x would keep on going like that. So the way that we write a piecewise function is we say, okay, there's two different parts. One part is minus x. And then we put a comma and say we only use that part if x is less than or equal to 0. Can we see that negative x graph we only use when the x values were less than or equal to 0. And we use the other piece when x is bigger than 0. And you only include the equal sign in one part. It doesn't matter which one. I could have put the equal sign in the second one and not the first one, because they happen to be the same point. But sometimes you'll have piecewise graphs that are disconnected, and then you'll have one dot filled in and one open circle, and be like, oh, you include the one with the filled in dot, not the open circle. Question?
This filter means like doing like way too much for no reason.
Well, it feels like way too much for no reason. However, would you agree that our range of that one was a little tricky because we had to add those graphs together? If we actually use the piecewise notation for h of x, right? So now I'm going to rewrite h of x is equal to, we had what, x plus 2 plus the absolute value of x. That was an explicit equation using absolute value. But if I rewrite it as a piecewise function, check it out. X plus 2 plus, well, let's use this part. When x was less than or equal to 0, what's the absolute value of x? Negative x, right? And when x was bigger than 0, I'd have x plus 2 plus, when x is bigger than 0, what's the absolute value of x? It's just x. This allows me to simplify this. It's actually really beautiful what's going to happen here. What happens with the first one? It just becomes x plus a negative x? 0. It just becomes 2, which matches up with our flat line. Right? Every single time x is less than or equal to 0, it's going to be 2. And what happens when I add these together? X plus x, that's going to be 2x plus 2 when x is bigger than 0. Check out our green graph originally, or purple, sorry. Do you see this has a slope of 2? Has y-intercept of 2? Then I can be like certain of those graphs. The piecewise actually makes me much more confident to say the range is greater than or equal to 0. Right? Like when I was adding them, I was like, is it always going to be 2? You're like, I don't know.
Yeah.
Checked another one, and you're like, there's a little bit of hand waving to say, oh yeah, it looks like it is, so we should just do it. This piecewise graph equation tells me for sure it's always 2 when x is less than or equal to 0. So it's kind of nice that way. So yes, maybe for the absolute value, since you already know what the graph looks like, it seems like more work. But for combining it with another function, it can be really, really helpful. Okay, that was a little bit of an aside of piecewise functions. Part C, oh, yeah, we've already figured out its domain and range. We've got the explicit equation. And for C, they want P of x. In fact, for P of x, I'm going to do the explicit equation, which was f of x, x plus 2 times g of x. And now I'm going to write P of x in the piecewise notation, right? We had one, because the absolute value switched when x was less than 0 and when x was bigger than 0. Well, when x is less than 0, the absolute value of x is negative x. And when x is bigger than 0, the absolute value is x. Okay? I want you to think what is easier for your brain to do. Option number 1 for graphing this is you know that, I want to make sure I've got my colors the same. I did green and blue. We knew that x plus 2 is this graph. And we knew that the absolute value was that graph. And your job is to multiply those together and draw me the graph. You could just take a bunch of points and do it and get a sense. But if I go to the piecewise notation, check this out. I'm going to simplify this. Okay. Oh, maybe I don't want to simplify. I like it. I'm going to like it like just like this. I'm going to graph it from my piecewise. And I'm going to color code again here. I'm going to do this part in purple and this part in orange. I'm going to start graphing that purple one completely. Do you see that that's a parabola? In fact, if you multiplied it out, I could say that it is negative x squared minus 2x if I distributed it equals y. That's a parabola. It's a parabola that opens down. What do I know about that parabola? Great question. Right? What do I know about that parabola? I have it in factored form. I know it has an x-intercept at 0, an x-intercept at minus 2. It has an a value of 1, which means it would go over 1, down 1. So I know my vertex is right here at 1, 1. If I graph the entire parabola, and I'm going to graph it with a dotted line right now, it would look like this. Opening down. So I'm using my skills from grade 11, factored form, using skills from grade 12 to draw that parabola. My orange parabola. What do I know about my orange parabola? It has the same x-intercepts, minus 2 and 0. But if I multiply this out, do you see that you would get x squared plus 2x? That parabola opens up. It has an a value of 1, so its vertex would be right there. And if I draw it on a dotted line, it would look like this. Now, what does p of x look like? Well, according to this piecewise graph, I have the purple graph, but only when x is less than or equal to 0. I'm going to do my final graph in green. Ready for this? So I take the purple graph from here. This section is the purple graph that I use. Because I only take it when x is less than or equal to 0. That's the piece of the purple graph that I take. Then the orange graph I take when x is bigger than 0. So you might be confused and think, oh, it looks like an x cubed graph. Not quite. Because actually, this is really sharp and pointy right there. If you would touch, I should not do it. You touch it, you prick your finger, it bleed all over the place. It's super sharp and pointy. Normal x cubed graphs and x squared, they're nice and round. You can tap them, they're fine. But that is super sharp point right there. It's called a corner in math. Corners are sharp. Okay? Or cusp. Sometimes a cusp, sometimes a corner. I think this is officially a corner, not a cusp. But to draw this graph, we just drew it perfectly because we knew what both those parabolas looked like. To actually think about taking individual points and multiplying them, it would take you, I mean, like, would you get that? Would you draw the sharp point? I'm not sure. So sometimes using the piecewise notation can give you a more accurate drawing of your graph as well. Okay, circle questions 3, 5, and 10.
So should you always use it?
Well, it's only going to come up with absolute values. All of your other ones that you put together, you can just distribute and you're going to get a regular polynomial. Like if you have a line multiplied by a parabola, you're going to get an x cubed graph.
Yeah.
It only happens with absolute value. And I have never, on the exam, seen them put an absolute value and piecewise together.
That would be evil.
It's not that bad.
For about like how many teachers teach their students this?
Well, maybe a lot don't. So then that would be evil for those. But you guys would be laughing. All these kids in these other schools don't know how to do these questions. That's really good when you get to the AP exam. You want other schools to do bad. Because then you don't have to do as good to do good. Does that make sense? Because everybody gets compared to everybody else. So good strategy before the AP exam is like go to other people's school that have AP, like burn their notes. Alright? Do things so they can't study. Because them doing worse will make you do better even if you do exactly
You
the
should
same.
leak the exam, leak a fake exam, and make it like so that everyone
Super
doesn't
easy so they don't
study.
study stuff.
Yes.
Good idea. And all these strategies for how we can learn next to nothing and still be the best.
Yeah.
Yes. Okay, that was on mute, so I hopefully that I don't get in trouble.